Hello and welcome to this wireless telemetry antenna lab tutorial. In this tutorial, I'm going to be covering the very basics of running CST Microwave Studio Suite, the software that we use to simulate and model antennas and other devices. So the first thing we're going to do is open up CST Studio Suite, which I just happen to have open because I'm running a tutorial. And we're going to come down here to 3D simulation, and then we're going to select high frequency. So to demonstrate the basic functionality of CST, I'm going to be doing the most basic sort of hello world type simulation, and that's going to be a 2.4 gigahertz patch antenna. So we've initialized our high frequency simulation. The next step is to come up here to the units, and we want dimensions to be millimeters. The frequency is gigahertz, and the time is on the order of nanoseconds. All the rest of these make sense, and they're grayed out anyway because they're not relevant to this type of simulation. So we hit OK, and now we're ready to begin modeling. So we'll come up here to the Modeling tab, and we're going to, in this case, create the substrate layer of the patch, or the dielectric layer. So it's easiest just to hit escape and enter all the values at once. So this will be our substrate. And really quick, before we continue, I need to open up the reference. So you'll go to, if you ever need to look at any examples or tutorials for CST, you'll go to File, Help, Help Contents. And this is where you can search for terms in CST. You can look at tutorials and examples that come with the software. You can look at documentation for the different types of solvers. So this is a really helpful tool for answering questions in CST. So as I mentioned, we are going to be doing this basic patch antenna, which is in CST Microwave Studio tutorials. And it is down here. So I just need this reference to remind myself about the dimensions. And so this document is doing a written walkthrough of this verbal walkthrough that I'm doing. So if you need to refer to any of the steps, or if you just don't like the sound of my voice, this is more than available for you to complete this tutorial. All right, so here is the size of our substrate. So we're going to go back here, 30 by 30, I think it said. Substrate, negative 30, 30, 30, 30, and then negative 0.7. And so in the next step, we want to define this material, which is going to be substrate. I believe it had a relative permittivity of 2.3. Let's check. 2.33, excuse me. 2.33. So this is a dielectric material, and so we wouldn't expect any kind of conductivity. So we're just going to leave that at 0. And then this is not a thermal simulation, so we don't need to fill out any thermal properties. But if we were doing like a coupled simulation or any kind of multi-physics simulation, we would need to fill out those values or we would get an error. The last thing I'm going to do is change that color slightly. All right, so we have substrate. We have all of our values defined. And you can, just as a sanity check, hit preview, and that will give you a preview of what it's looking like. Notice that it expanded the size of the working plane, so right now we're too far zoomed in. So the way that we can get around that is either scrolling out on the scroll wheel of our mouse, or if you don't have a mouse, you can hit the space bar. Select in your area, select in there first, and then hit the space bar. Okay, so it's come to my attention that I think my computer filter is on. So let me click out of this. Yep, there it is. Let's disable this just so we're not getting confused by the strange coloring. Okay, back to the tutorial. So we've defined our substrate layer. So the next step is we need to define the ground plane for this patch antenna. So the way that we're going to do that is we're going to hit Control on we're going to hold down the Control key on our keyboard, and then we're going to left click so that we can rotate this model around. And so you can see this ends up being kind of wonky. The way that you can adjust this is now hold down the Shift key, and that allows you to rotate this way. And then finally, if you hit Control and Shift together and hold them down, we can move this however we like. And I'll continue to refer to those commands throughout this video. I know it'll take a little while for us to get used to them. All right, so the next step is we are going to pick this face. So we hit Pick Points or Edges, double click. Now this area is selected. And then we're going to come up here to Extrude. And we want to extrude this area out. So this is going to be our ground plane. It has a height of documentation. Documentation is everything. 2.1 millimeters. Okay. And this is not substrate. This is PEC, which stands for Perfect Electric Conductor. And so now if we hit the Control key again to rotate back around, we can see that we've got this metal layer and then this green substrate layer. And you can also click and drag an area to zoom in so we can kind of see. So now I'll hit the space bar to zoom back out, and then the Control key and left click to rotate back around. And then Shift key to just rotate it a little bit more there, a little bit more sane. Okay, the next step is going to be creating the actual patch part of the antenna. So we come back up here, we're going to select cylinder, hit escape, and this is going to be our patch. Our patch has a radius of 23.2 millimeters. And unfortunately, I don't have these values numbered, so there's going to be a lot of back and forth. 0.07 thick. Okay. So once again, we can hit the preview button if we want kind of a sanity check. So that's about what we expect. So now we have our patch. So the next step is going to be defining the feed. So the feed is going to connect through all three of these layers. So through this patch, through the substrate, and through the ground plane. And our excitation signal is going to come in. You can imagine having like an SMA connector or some kind of connector that would screw in to this area. So we're going to have this hole. So we need to be able to model that adequately. So the first thing we're going to do is we're going to go over here to working coordinate system. Yes, that's what that stands for. We're going to go to transform. And because I always forget the numbers, we will be moving it up. So notice we have these dummy variables to represent. So U corresponds to the X axis, V to the Y, and W to the Z. So what this means is we're creating a local coordinate system and we're translating it up 9.2 millimeters. And this will make our lives a little bit easier. So 9.2. So that shoots up. So now we are going to define the feed, which is 4, 2.8, and substrate. Okay, hopefully you remember that. So cylinder, escape, outer radius of 4. And again, notice that the variable changes because you've created this local coordinate system. So we have this local coordinate system here, which is U, V, and W, and we have a global coordinate system here, X, Y, and Z. So just don't get concerned that the variables have changed. This is still fine. All right, minimum 2.8, I believe, and then it's substrate instead of PVC. Yes. Okay. And so now we're going to be warned. And the warning it's giving us is you have materials that intersect with one another. And so we can only have one type of material in one place at a time, right? So what this is saying is the new shape, the shape that we just defined, is the highlighted shape, and then this is the old shape. And so it wants to know, what do you want to do with this shape? So in this case, we want to add. Let me verify that we actually want to add. Yep, we want to add. And then now we're talking about substrate versus ground plane. And in this case, we want to insert highlighted shape. So we hit OK. And now, if we hold down Control and left click to rotate around, you can see that by using insert, we have removed this little circular area of this PEC ground plane, and we've made it substrate now. And that was that Boolean operation. And so whenever an intersection is detected, it will automatically prompt you. However, if you are modeling more complex structures, you can also come up here and do Boolean operations, so inserting or adding objects together to create more complex structures. That is for another tutorial though, so let's get back to this. So again, Control down and rotate back to where we were, so we can kind of see what we were doing. And so now we need to create the interior coax part of this. So we can go back up to cylinder, escape, and once again, I don't remember. What? This is what I hate about this tutorial, is they hide the number in here. So all the other ones, they've got the dialog boxes, and then for this one, they're just like, okay, 1.12 millimeters and an extension of 2.8. All right, so I'm going to make a mistake. So it should not be asking me this. And the reason it shouldn't be asking me this is because the material that this should be is PEC, but I made a mistake. So we're going to insert, call that, I don't know, experienced intuition. And so now we can come over here to components and see what we've done. So we've got this material that again is extruded all the way through. This is supposed to be the center conductor for this coaxial feed here. So you can kind of see, here is substrate, here is ground, and here somewhere is this material. Ah, that's right, I inserted it in. So this wire here is showing them. So anyway, how do we fix this when we don't have the right material? So you'll come over here, you'll right click, change material and color. We wanted this to be PEC. Come over here to PEC. And now this makes sense. Now we have our coaxial structure. So again, space to zoom back out. And now we are all done with modeling. We've modeled everything on this patch. So the next step is to set up the simulation. And so the first thing we need to do is create what is called an excitation port. And so this is a way of defining, here is how the excitation is going to come in. So remember I said that imagine we had like an SMA connector that would connect a coaxial cable into this antenna, and that's what's bringing a signal from our, say, electromagnetic generator. And so the way we model that from a simulation point of view is by creating what's called a waveguide port. So we'll go to simulation, waveguide port. You'll think about it. Okay. So usually there are a couple ways to create a waveguide port. So right now it is making the assumption that we want to do full plane. So that means a full plane wave is coming onto this. We can also define the coordinates of our excitation port ourselves. In our case, we don't want to do either of those things. So we're going to hit cancel. We're going to come back here to modeling, pick points, edges, or faces, whatever. And we are going to select this. So zoom in there. So we we've got this surface in mind. And so then when we go back to simulation, select waveguide port, it will automatically define a waveguide port where we've defined this pick, just how we wanted. So a couple things to note when you define waveguide ports. So most often the way that you will define waveguide ports is using a pick, like this method that we've just done. Not always, but most of the time. So there are a couple things you want to verify. First of all, this is just a simple coaxial structure. We don't need more than one mode, so leave this alone. It's defined the coordinates there for you, but again, they're set because we used a pick. And then you need to make sure this orientation is right. So it's difficult to see in this picture, but if we rotate, again, hold down Control and left click, we can zoom in here and we see that there is this vector. And you can't see it, but what it's trying to show you is that it is defined the direction of propagation in the positive direction right now, in the positive Z direction. And in our case, that's what we want. That's the direction of excitation to excite our patch antenna. But if it wasn't, we could select negative, and then you can see that we've got this little vector arrow showing us the direction of excitation. So again, in the case of this simulation, we want a positive excitation. So we'll click OK. And spacebar to zoom back out. And then let's rotate back around. So again, it's holding Control down. And the next thing we're going to do is actually set up the solver. And so it's going to ask, all right, what frequency range do you want to run the simulation over? So I said at the beginning of this tutorial that this is a 2.4 gigahertz antenna. And you get a gold star if you know what's special about 2.4 gigahertz. So we're going to run it between 2 and 3 gigahertz. And again, just to verify, oh, hang on, verify in a second. So usually for this lab, we will usually do simulations between -40 and -50 dB. So the further down you go, the more accurate it is, but the more time it will take. So we're going to leave it at -40. And then very often we will do adaptive mesh refinement. I'm curious if they have us do it in this tutorial or not. We've moved down quite a bit. Interesting. Okay, so I'm going a little bit out of order at the moment. So we're doing this step now. All right, so it doesn't do adaptive mesh refinement, but what that means is for future simulations, we can go to Simulation, Global Mesh Properties, and this shows what the mesh properties are, but more importantly, if you go to Mesh View, you can see how it's defining the mesh. And so what that means is that it solves this electromagnetic problem for each of these little areas. So it's this iterative process. I believe it's based on the TDT model, but I'm not certain about that. Anyway, so close Mesh View. Back to the tutorial. Stay focused, Katie. Okay. So I will do things in the order that they want to do things. So they want us to define the boundary conditions first. And so boundary conditions are essentially a way of telling the simulation what exists at the edge of the simulation model. And so in the case of this patch antenna, we are going to do, what are we going to do? Open, 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 and then the Z direction, which remember that's the direction of propagation, is where things get interesting. So we will do electric here, and do open add space. So I'm not going to get into why these boundary conditions are what they are in this video. I'll probably cover more about boundary conditions in future tutorials. I think I'm going to leave it at that. So for now, just trust me in the software that these boundary conditions make sense. You're going to hit OK. So now the boundaries have been defined. The next step is to define our monitors. So what do monitors mean? So if you go up to simulation, select field monitor. So we see there are a bunch of different options. So we've got electric field, we've got magnetic field and surface currents. We've got far field, so again the far field currents, but also this is going to show you your radiation pattern. Power, current density, SAR. SAR is very important when you're talking about biological applications, since SAR is heavily regulated by the FCC. So we are going to do electric field at 2.4 gigahertz. And so all that means is we want to solve the electric field at 2.4 gigahertz in operation. So we got that. We also want a far field. Or maybe it only wanted a far field. We're going to do an electric field too, because electric field is interesting, and I actually use that one much more than far field. Anyway, I'm staying focused, I promise. Far field, 2.4 gigahertz. Alright, so we've defined our field monitors. We've done our boundary conditions. Last step is to verify this thing that I kind of did out of order, which is we're doing a time domain solution of this electromagnetic problem. And so in this case, we're going to do a hexahedral mesh, -40. And in this case, the source type is all ports, because we only have one port, because this is an antenna and it's radiating. When you get into things like transmission lines or more complex structures interacting with each other, you'll need to define the source that is being excited, is what that means. So all ports, doesn't really matter. You could also just say the port that it is. So let me just verify that. So see, I could say port 1 if I wanted to. In this case, it wouldn't matter. And so we hit apply. We are now ready to run the simulation. So hit start, and oh, we have an error. This is exciting. Okay, far field monitors are not supported. Okay. One last step that I forgot about. Go to background. Right now the background is specified as PEC. This is not what we want. We want to specify normal. So not conductive. Specifically, something that is useful is you can go to properties, copy properties from material, and we want the properties to be air. So this means that background material, anything that's not what we've defined specifically, is air. I'm glad I got caught with that. Alright, so we hit OK to all of that, and now we're ready to run the simulation. Hopefully. Second time's the charm. Let's see. Alright, so get started. That concludes this video, and we'll check back in on the next video where I will go over the results of this simulation as well as some helpful things for viewing results and creating results for conference papers. So, see you then.